today we're gonna run volatility model. Suppose define sigma n. Sigma n as volatility per day between day n minus 1 and n as estimated at the end of day n minus 1. And let's define as I the value of the market variable at end of the day, such as the stock price. Then is the if PSI is stock price, then UI log SI minus 1, which is the continuous version of the return. Right? And then the simple standard deviation is actually daily volatility. It's the first very naive estimate of the daily volatility where U bar is just average. And then next, another possible approach, we can define UI is the SI minus I divided by SI minus 1, and assume the mean of UI is almost 0 because it is daily return. So daily return should be very close to 0. Right? So maybe it doesn't matter. So assume that the mean value of UI is 0 and replace m minus 1 m. And then it is slightly different, but actually the value of this one should be very similar to this one. Okay? And the weighting scheme. One problem about this approach and this approach is that, as you can see, we give equal weight for all the sums. But intuitively, we want to give more weight to the least one and less weight to the old one. So instead of assigning equal weight to the observation, we can set sigma n square I minus 1 to m alpha I u n minus I square, where this is 1. So it is weighted average. So intuitively, we want to give more weight to the recent observations. And the RGM model is the, I don't know why it is. In an RGM model, we also assign some weight to the long run variance rate, VL, such that sigma n square is gamma VL plus this one and historical average, where gamma plus sigma alpha I equal 1 should be 1. Where VL, we can think of it as like a long run average. Sometimes we use this one for like just simple standard deviation, for example. This is called arch model. And then UMA model. UMA model is in an exponentially weighted moving average model. The weight assigned to the U square decline exponentially. So as we move back through time, so this leads to sigma n square is weighted average of the volatility of yesterday, Fourier volatility yesterday, and the innovation of the yesterday. Okay, so yesterday we set up from our model we have some estimate of the volatility, and then there is an innovation or shock. Yesterday's stocks, so maybe we can use average of those two, weighted average of those two. It's a UMA model. And then if we use UMA model, it is actually exponentially, the weight are exponentially decreases, so you can see it very easily. So sigma n square is lambda at sigma n minus 1 square plus 1 minus lambda u n minus 1 square, right? And then this sigma n minus 1 square is lambda sigma n minus 2 square plus 1 minus lambda u n minus 2 square, something like that. And then we expand it, and it becomes 1 minus lambda u n minus square plus lambda 1 minus lambda u n minus 2 square plus lambda square sigma n minus 2 square. And if we keep doing that, then we have sigma n square is like weighted average of u n minus 1, u n minus 2, blah blah blah, very long, relatively long time ago. And then as you can see, lambda 1 minus lambda and lambda both of them, lambda is because it should be between 0 and 1. You can see the weight for the squared return should decrease exponentially. So it gives something intuitive. It gives us what we want. We want recent innovation more weight and old innovation less weight. Okay. We want the square of the recent returns more weight and the square of the old return less weight. So this is in line with it. And the attraction of UMA is that relatively little data needs to be sorted, and we need only remember the current estimate of the variance rate and the most recent observation of the market variable. And it tracks volatility change. And one popular choice for lambda is 0.94. So if we put lambda 0.94, then actually we give another way to the pattern, okay? Yes, the volatility, and just to shock to the yesterday, we give relatively small weight. And then the important one is Garch. Actually, we will gonna run Garch. We will focus on Garch. In Garch 1-1 model, it is a combination of Arch and UMA model in some sense. In Garch 1-1, we assign some weight to the long run average variance rate, so sigma n square. So volatility of today is gamma VL, which we can long run volatility, and alpha u n minus 1 square and beta sigma n minus 1 square. Okay, so it gives weight to the three things. Okay, three things. Okay. Such that first we give weight to the for example like a sample very long run volatility, which is not time varying, and we give another way to the shock of the yesterday. U is a return basically, square of the return yesterday. And then we give another way to the volatility we estimate yesterday. Right. So in some sense, it is the beta is consistent, it is the persistent part. Beta measures how volatility persists over day, and the alpha measures how volatility affected by very recent data. Since the weight must sum to 1, so it looks like this. And then we are focused on Garch. And then setting omega as gamma V, the Garch 1-1 model, because sigma n square omega alpha u n minus 1 square plus beta sigma n minus square, where VL is omega 1 minus alpha minus beta. Okay. And for example, suppose this is our model, such that sigma n square is 2 plus 0.13 u n minus 1 square plus 0.86 sigma n minus square. So long run variance rate is this one, 0. So long run volatility per day is 1.4%. So suppose that current estimate of the volatility is 1.6% per day, and the most recent percentage change in the market variable is 1%. Can I? No. 1%. Okay. Then it is a 0.000002 plus, because it is the our first coefficient was 0.13. 0.13 multiplied by, since the most recent change in the market value, stock return was 1% like yesterday, so it is 1% is 0.01. So square of that one is 0.0001. And then yesterday current volatility is 0.6%. So if we take square root of the 0.6%. Actually, we have to square it. If we square 0.6, then it becomes, so our new variance becomes this one. So it is a volatility, it is a sigma square. So if we take a square root of this one, then it becomes 1.53% per day. Okay? Any questions? Of course, I will show you how to estimate this one, but anyway, somehow we estimated today's volatility today's volatility, and we put the square of that one, and if we know today's return, and then we square it and put it here, and then if we use formula, then we know what would be the volatility of tomorrow, something like that. So if we know volatility of tomorrow, then we plug this one again here, okay, and then square it, and if we observe stock return tomorrow, and then we square it, and then plug this one again, then we will get the volatility the day after tomorrow, right? It is something like this. So it is iterative. And then actually we can generalize Cauchy-1-1 model, and the Cauchy-PQ model is we give weight, okay? We take into account the P, okay? We take into account the square return of the last P period, and then we take into account the volatility of past Q period. Okay, and then the question is, okay, now we have a volatility model. If we have a good volatility model, then maybe we can estimate what would be, we can guess more correctly what would be the future volatility price, something like that, right? Future option price. As you remember, when we use the call and put option price, the only thing we need to estimate is the volatility. And then we can use like a Cauchy model, okay, to estimate the volatility, and then we can plug that value into the, for example, our option model, and then we can calculate option prices. Okay, so it's done. The last question is that, okay, how we can estimate this one and this one and this one? Okay, how we can estimate omega, alpha, and beta? Okay, that would be the question. In order to estimate omega, alpha, and beta, we use a method called maximum likelihood estimation. Have you ever heard of the maximum likelihood estimation? Did you? How about you, Felix? No, never heard of it. Maximum likelihood method. In maximum likelihood method, we choose parameters that maximize the likelihood of observation occurring. Okay? So in this model, there is the unknown parameter, omega, alpha, and beta. And our goal is to choose omega, alpha, and beta such that we maximize likelihood, roughly speaking, of actually observing the data, current data. Yes?
I don't know what the name of the letters times VL. Is that the omega?
That is a gamma. Okay?
So
Gamma times V, right?
that is omega.
Omega, yeah. Because there is a constant of two things. Right? So again, in maximum likelihood estimation, we want to choose omega and alpha and beta such that we want to maximize the probability, roughly speaking, probability, more rigorously speaking, likelihood of actually observing the data. Data is what we have, right? So what kind of parameter will make the current data set most likely to appear? Okay, that is the framework. Then we have to define likelihood, right? What is the likelihood, actual likelihood, or roughly probability of observing the data? Example 1, I think this is a good example. Example 1. Suppose we draw coin. We toss a coin. We observe that a certain event happened one time in 10 trials. So for example, we toss the coin 10 times and we have only one head. Okay? Suppose that is our data. We toss the 10 times and we have one observation for head. And then in the maximum likelihood estimation, what we want to do is basically we are interested in estimating probability of observing head. And then usually in the fair coin, it is 1/2, right? If we toss fair coin, the probability of the head should be same to probability of tail, so it is 1/2 and 1/2. But then we toss the coin 10 times. Actually, we toss the coin, and 10 times we have one head. Okay. So from that data set, we want to estimate the probability of actually having the head. Okay. To turn around that argument, our goal is to find the probability of having a head that maximizes the likelihood of actually observing that 10 outcome in which we have only one head and we have 9 tails. Do you understand what I'm saying? 무슨 말인지 알겠어요? 그렇죠? 어떤 확률이 뭐면, 확률을 뭘 선택하면, 그렇죠? 이 동전에서 앞면이 나올 확률이 뭐면, 그렇죠? 과연 한 번 헤드고 9번 테일인 그런 이벤트가 가장 많이 일어나겠느냐, 일어날 가능성이 제일 높겠느냐라는 거지. What is the probability that maximize the event that we observe, in which we have only one head and we have 9 tails? What is your guess? What would be the probability? That probability. 1/10?
Because, I don't know, when we think about it, maybe it's just our thinking that it's 50%, but maybe it's a different coin, or we always have the same mistake when we make the experiment. So we have to say...
Oh, yeah, actually, there is the answer. Yeah. So, yeah, actually, our case is that if we draw coin 10 times and if we have only one head, then we can suspect that it is not a fair coin, right? It is maybe the fair coin, but if it is a fair coin, that event is unlikely, not so likely. Only one head is not so likely. So we guess that the probability of having head is less than 1/2. But definitely it is not 0, right? If the probability of having head is 0, then we don't expect we observe head, but we have at least one head. So we conjecture that the probability of having head between 0 and 1/2. Okay, 0 and 1/2. And we have to find one specific probability in that region such that that maximizes the actual occurrence of this whole event. So we can do it. Let's assume that, let's denote the P as the probability of having head when it toss a coin, P. And then we have one head and 9 tails. So probability of observing that event is P multiplied by 1 minus P9s, right? It is actually the probability of the event that we observe. And then we want to maximize it. We want to choose P, then maximize this one. And then this one, it shouldn't be difficult. Okay, so suppose P is the probability of the head. Probability of head. Head. And we have only one head, P, which means that we have 9 tails. 1 minus P9. 9. And then we want to maximize this one with respect to P. But then it is a power thing, and then if we take log of this one, then I think this problem getting easier, right? Log is actually increasing function, and so simply maximizing this one with respect to P is the same to maximizing log of this one with respect to P, right? Because log is increasing function. So this is same to max of the P with respect to log of P 1 minus P 9, right? They should be same, right? Because log is increasing function, okay? if P maximizes this one, P should maximize this one as well. 네, 질문 있어요? Right? And then this one is log P plus, right? Log is such a convenient 9 log 1 minus P. This is the beauty of log, right? We can change multiplication into the sum. We can change division into the minus, right? This is beautiful. It is much more convenient. So how we can calculate, how we can maximize this one with respect to P? How you can find it? What? Yes, differentiation, right? We take derivative with respect to P. What is the derivative of log P with P? 1 over P, right? So if we take derivative of this one, then this is 1 over P, right? Plus, actually there is minus over here, so minus 9, 1 over P. And then we want to find this one 0. Then if we multiply P, 1 minus P each side, then 1 minus P equals 9P. So P is 1 over 10. So this is exactly in line with our intuition, right? We toss coin 10 times and we have only one head. So our intimate guess, well, maybe the probability having a head is 1/10. Actually, that guess is in line with the maximum likelihood estimation. When we have probably 1/10, that actually maximizes this one, which means that we maximize this one, which means that we are maximizing the probability or likelihood of actually observing that outcome. This is called maximum likelihood estimation, and it's very, very convenient, very, very appealing one. Right? And then about estimating volatility, when we are gonna estimating volatility, okay, then okay, the probability, suppose we have a volatility, we have time varying constant volatility, estimate the variance observation from a normal distribution with mean 0. In case of standard, in case of normal distribution with mean 0, then observing one data, one return, likelihood of observing one return looks like this one, right? Because it is not exactly probability, but it is a probability density function. So this part is actually the likelihood of observing I's outcome, right? Data UI, okay? UI is the return, right? And then we have data from I equal 1 to M. Actually, we have to multiply them all, right? So this is a probability, actually not exactly probability, again, it's a probability density function. So actually, this is the likelihood of estimating our whole return. Whole return. Of course, we don't know what is actually V over here, which is sigma square. Look, in case of normal distribution, right? In case of normal distribution, we know that probability density of normal distribution looks like this, and we denote sigma square as the V, okay? V over there. So we change sigma square. We change sigma square as V. So we put this one inside, so V, and then mu is 0, right? Like daily return is close to 0, so it is 0. So that is exactly the same to this one. So it is this part, this one over here, is a probability of actually one data. But we have whole data. We have data of daily return for the last m days, right? For the last m days. Therefore, this is all joint probability, and then the way to getting the joint probability multiplying each other, right? Like a 10 coin in the previous case, we are multiplying probability of each event. One head, and then 9 tails, so 1 minus p. We keep multiplying that, right? So it is joint probability. We are all multiplying that out. So our goal is here to maximize this v thing. We make a v, which is a variance, then maximize this one. But then again, this is the multiplication, and then multiplication is less convenient than summation, so we take log, right? So if we take log of this one, then this one, this multiplication part is a summation conveniently, and taking log of this one over here is exactly the same. Okay, so if we take log over here, then log of this one is the actually minus 1/2, right? Right? Minus 1/2 log ln. So it is the, okay, ln one, right? So this is actually ln. So it is the 1 over 2 pi plus ln v분의 1, right? Then this is constant. In constant, when we maximize with respect to v, okay, we want to change v, then maximize the whole thing, okay? This is constant, so we don't have to take into account this one, right? This is not a function of v, so we don't have to, we can ignore this one, right? Because it's simply constant. And but this one includes v, and this one is a minus 1/2 log v, right? And then about this one, if we take log, then it is simply I square over v, right? But then it is 1/2, right? 1/2, and we can simply multiply 2, and then it is still same, right? We can multiply just constant. So in the end, what we have is that maximizing this complicated thing is actually same to maximizing this one, this simple thing, right? So we want to find this nu. Actually, it's Greek nu, but let's call it just v because it's similar to v. So we want to find actually v, then maximize this whole thing, right? 무슨 말인지 알겠어요? Do you, Felix, can you understand what I'm saying? Nicholas, 여기 김밀령 학생. Yeah. So okay, then let's calculate this v. Then again, we take derivative. Then if we take derivative, then we have a summation, and derivative this one is 1 over v. And then if we take derivative of this one, well, it is a bit complicated, okay? But it is the, okay, minus 1, so it is actually v square, okay, v square, and then ui square. And then it becomes plus. Okay, if we take derivative of this one, and then we want to make this one 0. Okay, then we have a square, and then, well, we move this one each side, then it is the same too. Summation of 1 over v equals to summation of v square over ui square. Right? And then let's multiply v each side. And actually, if we multiply v each side, then we have only 1. Right? Then what is the summation of 1? Is m, right? We add 1 m times. So actually this part is simply m. So we move v over here, and divide each side m, then we have this one, right? So if we have very intuitive one, okay, so the likelihood of actually observing the data given nu, given v, and then we want to find v that maximize the event we are observing, this is simply sample variance, right? This is exact, it is almost same to the variance. Okay, in the actually variance, sometimes we, instead of using this one, we sometimes use m minus 1 over here, right? Divided with m minus 1. But actually in the maximum likelihood estimation, dividing with the m is even better. Okay, so it is like a sample variance. So the maximum likelihood estimate of the v is actually sample variance. Okay, which is exactly what we learned. Okay, we learned the variance is important, and then there is a variance, and actually that is justified with the maximum likelihood of estimation. Okay, so okay, this part is easy. Okay, we are assuming that this v is not time varying, but what if v is time varying? What if v is time varying and follow like a Cauchy 1-1 model? Okay, that would be a bit harder, right? But that is not difficult. We use exactly the same framework. Okay. Now, in the application of Cauchy, all we have to do is, okay, it is almost the same problem, but all we have to do is now this volatility is time varying. If volatility is time varying, variance is time varying, so we have to change I over here. That is the only difference. In the previous case, we assumed that volatility is the same, but now it changes every day. Okay, so this is the only thing we can change. Okay, over here, right here. So we cannot use this one anymore because it changes every day. Okay, this one, we choose parameters that maximize this one. Okay. And how to do that? Okay. Well, we have a model, so we know what is the Cauchy model, and then Cauchy model is over here. This is our Cauchy model. Okay. This is our Cauchy model. So our idea is that first start with any omega, alpha, and beta. We can start with anyone, for example. And then for any arbitrary value, this one and this one, this one. And then we can fill the volatility of each day, right? Volatility of each day. And then given this one, we have observation of this one and this one. We have update for next variance. And then we have next variance and next return, and we have update for next variance, something like that. So we can fill the variance each day. So we can calculate this one for each day. Therefore, we can calculate this one. And then next, we can use Excel solver. We can use Excel solver such that maximize this one with respect to omega, alpha, and beta. Right? Then we are done. Important note. Set up spreadsheet so that you are searching for 3 numbers that are same order of the magnitude. Yeah, same order of the magnitude. That's a good one. But anyway, yeah. So in this case, there is a simple Excel application, one example. So suppose this is the date, and then day 1, and then we have how many data? We have 1,279 data. We observe data from July 18, year 2005 to 13 August, year 2010. So we have data. We have it is what? It is daily data. When we have 1,200, almost 1,300 data. Okay. In the data, we have return. The historical return is This is stock price. Let's assume that S&P 500 index date is something like this. If index values is looks like this, then we can calculate what? We can calculate the return every day. Okay, we can calculate return, something like that. Okay, with return something like this, and then given our initial guess about omega, alpha, and beta, and we can fill the VI for each day, and if VI and UI, and we can calculate log VI minus UI square VI, something like this. And then we can sum them all, we can sum everything, and this is sum of entire thing. And when we maximize this one by choosing omega and alpha beta. Okay? And then one important is variance targeting, and then we will do variance targeting, but yeah. Okay? And then we can go to actual example. Okay? Actually, I kindly developed the spreadsheet. So you can open your computer and go to our course webpage, and you can download this Excel file. Let me upload this one. Interesting. Delete. Remove. I want to share today's presentation first. No, not this one. And then I want to upload first. Yes, but I think this is better. And open the Google slide. It should work now. But anyway, while I am waiting, it still takes a lot of time. Okay, it now work, and then share, get the link for this one, copy, done, and then instead of this one, I'll put this one. And then I'll change the slide more, okay? Because of copyright issue. I have to change the content of the slide. Okay, but anyway, yeah. Okay, so open it. And then in my data, actually, this is data set. Okay, second set is the data set. So in my data set, I have a inverse order. I have a kind of inverse order. So old one is in the bottom, and the least one is in the top. Okay, so yeah. So actually, I'm gonna use this one. Okay, so in our data return is basically. Okay. Why? They are actually same. Okay. So anyway, this is UI. UI is, for example, this one is, what I'm doing is this one. Okay. I'm dividing in the textbook log of this one. No. Yeah. Because it is actually, I already have return data. They are all return. But it is a percent return, so I want to divide this one by 100. So then I divide this one, because it is not price, I already have return. So if I divide this one by 100, then I have this one. Okay? And in order to change it to continuous return, what I did is I simply did is a log 1 plus this one. Okay? Then I have a continuous version of the return. Okay. Actually, it doesn't matter whether we use this one or this one, but I'll use this one because it's a continuous one. Do you know what I'm saying? Okay. Because we have a data in our data, which is already this form. Our data looks like this one already. ui minus 1. And then it is discrete, so I want to change it, so this one is like r. And then we want to change r as a log 1 plus r. Then it is like a continuous one. Okay, so we are going to use this one. No, not, yeah. We're going to, yes, so this is actually u. Okay, so this is actually u. So I'm going to this u to estimate Garch model. Okay, Garch model. And then if we plot the data looks like this. Okay, so sometimes it moves a lot. Okay, and if we estimate Garch model, let me show you the data. If we use Garch model, the estimated volatility looks like this. So in the Garch model, volatility should change every day, right? Volatility is how they change every day. So in the Great Depression, volatility spiked, and then the Asian financial, this is around Asian financial crisis, I think, somewhere here is a spike, and it's the Lehman crisis, is another spike. So it captures, right? This is beautifully captures the time varying volatility. So we want to estimate this on Garch model. So how we can do that? This is actually, I wrote, this is Garch 1.1. This is another called the E-Garch model. This is another one called the GJR Garch model. Okay. Actually, in stock market, instead of Garch model, E-Garch or GJR Garch is more popular. In the FX market, Garch 1.1 is more popular. Therefore, I'm showing everything. Okay. But let's start with Garch model. Here, my notation follows Wikipedia. Okay, in the Garch model looks like alpha 0, alpha beta. Okay, so first one is RV. Oh. Anyway, this is alpha 0. And then because sum of this one should be 1, which means that sum of this one, okay, sum of the alpha beta should be less than 1, right? Because this is weighted average, right? So sum of this one and this one should be less than 1. So sum less of this one should be less than 1. It is from this one. Okay, in the Garch model, because this one gamma alpha beta should be summed to 1, right? Which means that alpha plus beta should be less than 1. Okay, so I want to check whether this is less than 1. And this V0 is just a sample variance. Okay, this is the standard deviation, and this is sample variance. Okay, so this is from over here. So let's say this is like standard deviation, STDEV, of this entire thing. This one. Oh, sorry. Three. Okay, and the mean is the mean average. Average of this one. Anyway, this average is very close to 0, right? So I'll assume this is close to 0. This is 0. And this is 0. And then volatility is the square of this one. So no, this is the standard deviation, and daily variance is square of this one. It looks like this. Okay, now we start with the volatility model, our volatility model. But before I do the volatility model, I use something called the variance targeting. Variance targeting. Okay, in Garch model, okay, Garch 1.1 model. Let's go to the Garch 1.1 model. Garch 1.1 model. Okay, in the Garch 1.1 model, basically we have to estimate this one and alpha and beta. We have 3 parameters, right? We have those 3 parameters that maximize likelihood. But actually estimating, maximizing over those 3 parameters is fine, but actually a lot of people do is some trick. Instead of maximize over 3 variables, okay? Some people actually to the optimize over only two variables by using techniques called variance targeting. So let's put variance targeting means let's put n becomes infinity. Okay, let's put n becomes infinity. Then sigma n square will converge to sigma square, something like this. Let's assume. And then this is gamma VL. Okay, and let's write down just here, gamma VL plus, then if this is infinity, then this one would be something like this one as well, right? Because this one is anyway summation. Okay. Another idea is actually we can put expectation over here each side. Okay, I think that would be better. That would be more intuitive. Okay. Let's us take expectation both sides. Okay. Let us take expectation both sides. Over here, take expectation over here, expectation over here. Then expectation of this one, okay, it should be sigma square, right? We can drop n. So it is sigma square. And then this is sigma square. We don't need this one. Okay. And then gamma V plus, if we take expectation of this one, then it is again the variance, right? So alpha sigma square. And then beta sigma square, right? Then about this one is something we have to estimate, but this one is actually, we have 1 minus alpha minus beta sigma square, right? We can guess that this one should be sigma. So we can, if we use this technique, it is called variance targeting, then we don't have to do the maximization over three things. Instead, we can do the maximization over only alpha and beta, which is much more stable. Okay, maximizing over three variables, sometimes maximizer Excel solver doesn't work. But if we do the optimization over only those two alpha and beta, then it converges to a desired value much more quickly and generates much more intuitive value. Okay, so in our Garch model, okay, this is our Garch. So RV is simply 1 minus this one, and then this one, I9. Okay, okay. This is 1 minus this one, parentheses, and this one square. So it is variance targeted. Now we can optimize only with respect to this one. Okay, and let's say our initial guess is 0.2 and 0.2. This is our initial guess. And alpha plus beta 0.4, it is less than 1. And then, okay, from this one, okay, from our initial guess, now we can calculate the V, right? Then V is the, right? Then what we can get is the V is first this one, okay, plus this one, beta, multiplied by, okay, let's start from in our equation. Okay, we have alpha first, beta alpha first. So we have alpha multiplied by u square, yesterday's u square, plus now beta multiplied by yesterday's beta. Okay, something like this. But we don't have yesterday's beta yet, right? But if we can fill this one continuously, and then okay, we can fill update this one. You can fill up to this one. But then we need the very first one, right? Because we need a V in the very first one. we need V in the very first one, so we can fill the others one, right? And for the very first one usual trick people use is that very first one, not surprisingly, we can simply use another sample variance again, okay? We use this as a starting value, okay? So from this one, we can fill the variance, right? Everything, right? And then from this one, now we can calculate likelihood function. We can compute likelihood of observing each data, which is, okay? 김일리 학생 졸린가? 졸려? We can use this one. So ln v minus u square divided by v. This is the likelihood. Okay, this is likelihood. And then we want to calculate this one every day. And then we want to sum it all. Likelihood sum. This is sum of this entire likelihood. Okay, sum of this one. And then we want to maximize this one with respect to our alpha and beta only. Because I did the variance targeting, so I can use this one. So I can do the data. Yeah.
Is from today's variance or
What do you mean by?
yeah, for weeks or yesterday variance, right?
Yeah, it is
But
for likelihood. Yeah, I use because I'm calculating likelihood of today's data. Therefore, I have to use today's volatility, which is I don't know. I know this one given the yesterday's volatility, of course. But yesterday's volatility should be conditional on today, before yesterday's one. So it's a key update. So what is what?
judging by the formula for V, in here you have the large alpha times D2 raised to D2, and there you have D3 squared. Not for L, but for the V formula. I don't know if you really wanted to change it or if you just wanted to show us how we
Change what?
the formula for V.
Formula for V?
Yes, exactly.
This one?
Before you had large alpha times D2 squared, and now you have D3.
Oh, really? D3. Because there is a slight mismatch between, okay, alpha and then, so let's use this one because it's in Wikipedia. I have to multiply alpha and epsilon square and beta and sigma square. So in the Excel sheet, can I take a look at it? In the Excel sheet, I distributed. In the Excel sheet,
Because you were on the top one, right? Because here's
Yeah.
with D2.
D2 square and E3.
Exactly.
I think that was wrong. Used path.
Maybe there is a mistake, but I think this is right. This is the right one. Okay, I have to use yesterday's U square, right? Look, our Garch model looks like I have to multiply yesterday's this one and yesterday's one. So there is a small mistake in my Excel sheet. I'm sorry, but you can change it. Okay. So then, well, next one is very easy. We can do the 해찾기, solver, and then we target this one. This is our target. And then I want to change this one. And then our okay, I did it for convenience, but and then what I want to add is that I want to make it sure that this one, sum of alpha and beta should be less than 1. But I usually do this one. Okay? Because there is no, in Excel, there is no like strictly less than 1, right? It is less than equal to. So therefore, I have to make it like a 0.99999. Okay? And then I have to run. Well, I developed a code, so let's run this one. So, okay. Well, this is different from the previous answer. Wow, what's wrong with this? Whenever I run it, it looks different. So, yeah. (38066) right? This is not, well, even if I did variance targeting, the answer is not that appealing because it is minus 37. Oh, I think this looks okay. Minus 37, something like this. So, okay, I got the answer. So, actually, my VBA code for this one, the VBA code Karch is that this is Karch. Karch is the solver is set, and the precision is 0001. Let me increase this one. And then my target cell is my target I10. I10, this is my target. Okay, this is my target. And I by change, and the maximum value I want to maximize, and by change I6 to I7. I6 to I7. I am by change this one. Engine, optimized engine, non-linear algebra. So, and then I have a bunch of restriction. Okay, bunch of constraint conditions. So first, this one should be less than 1. I8. I8, this is less than 1. Okay? This should be less than 1. And then actually for make my numerical analysis more convenient, I added another one. This is not essential. You don't have to actually add this one, but I added them for convenience, for just in case Excel does not work, because Excel solver is not good. So I says that I8 is this one. So this is less than 1, and I6, this is the greater than equal to this one, because intuitively this should be positive. Intuitively this should be positive, so I want to make it positive, and intuitively this should be positive too. And then this is positive, greater than equal to 0.0001. And then third one is that I want to make sure that this one and this one, both of them are less than 1. Actually, they are not that. Sum is less than 1 and each one is greater than 1, then naturally both of them should be less than 1, right? But I want to make it sure again that they are, each one is less than 1. So I deliberately added the unnecessary, 4 further unnecessary conditions to make Excel work more correctly. But actually they are unnecessary. But if we don't, if I don't add this one, because Excel solver is not good, Excel solver is not good. Sometimes solver doesn't work well. Well, now it works, but yeah. But this is optional. But I usually add this one because, yeah. Okay. So if we estimate Karch this way, then we have this again historical data, and I have my beautiful estimate of the Karch like this. So it looks okay, right? It looks beautiful, right? This is how stock moved actually, and it is my estimate of the volatility for each day. And they are time varying, clearly time varying. In the data, we can see that volatility is time varying. Volatility is not constant. Sometimes market volatility high, sometimes market volatility low. And my Karch model, exactly Karch 1 month model, exactly captures that one. And next 2 weeks, next Wednesday, we will run eGarch. If we use eGarch model, when we have more dramatic. And then GJL Garch is between this one and this one, less dramatic. Okay, so next Wednesday we will learn eGarch and GGarch. But before doing that, you can go over this code because it is very fun.